Hello, folks. Welcome to the session 4 applications session. Hi, folks. My name is Shayan, and I'm from PNNL, and we are going to now hear two presentations about novel usage of MPI on applications. And the first presenter is Julien Jaeger. Thank you.
Okay. Yeah, okay. Great. So today I will talk about enabling global MPI process addressing in MPI applications. So first, as an introduction, I would like to thank Martin and Tony because some slides in Martin's presentations, also Tony's questions yesterday really helps also to introduce this work. So what we've been working on for a few years now with Jean-Baptiste and the other folks at CN Power Tools is trying to use MPI as a way to use composability and to use MPI services. So trying to make MPI evolve and see how we can use MPI to just launch and connect services between them when we are losing jobs. So I think it really relates to what Martin was saying yesterday, that we need to break HPC dogmas. For example, on one node, we have only one job. We know that it's kind of difficult now to do this in an efficient way. And also, one of Tony's questions to Martin was, can MPI do better on workflows of jobs? And really, this work try to tackle that. Not having only one job that launch with a static set of resource, but having multiple jobs working together, connecting together, and to give the full picture and your full applications. So first, I will talk a little bit about what we call scaling vertically. So when you program applications, nowadays, you will use multiple models. So most of the time it will be an MPI plus X plus Y and plus even other programming languages, because you will need strength and you will need maybe something to tackle your accelerators. And as we have said also, we have machine learning stuff going on, AI stuff. So that may needs also additional programming model that will come into the mix. Also, we need to tackle multiple hardware. So it's kind of more and more difficult to really have, we don't have this monolithic view anymore. We have really a lot of different things to compose and to run on different hardwares, which is very difficult. Also, it's very difficult because most of the times there is very few collaboration between the libraries that will tackle the different resources or that will implement the different programming models. So basically what we end up is something like that. On the upper end, you will see a program that will use a bunch of different libraries, some IO backends, and they will rely on different runtimes. So pthread, MPI, OpenMP, CUDA, ROCm, and so on and so forth. And that we have to schedule in so the different hardwares. The problem is it's really difficult to schedule that efficiently. They will compete for resources. So you will have the resources that will be used by programming models, which is not really the one that you want to schedule right now because it's not the one with the most things to do. And basically, when you talk to people programming applications, you will end up with, okay, I had to hybridize my code with OpenMP. And now we are told to target GPUs. So In my program, I will call library A, then I call library B using the programming model X. Otherwise, I just can't tackle. So I just take the pieces that I need to work on my supercomputer. The thing is, when I do use some libraries and component like Y, I don't know what it does internally because it was programmed by another people or another. I have really no idea what's going on. And when you goes to the runtime, you run everything, and basically, okay, let's hope it goes well because I don't have any means basically to try to make them all work together. So I will mitigate that a bit. We do a lot of efforts in different application programming models to try to know that some other runtimes is using the same hardware. So we'll try to improve that. So all this composability will be better off vertically, but it's really something hard to do. So one solution may be to scale horizontally. So by scaling horizontally, we mean what Martin was saying, but breaking the HPC dogma. So we won't just have one jobs calling a lot of things and all running on the same hardwares, but maybe just cut into pieces for each pieces to use a specific set of hardware. So here we can see, for example, that program will use only 2 CPUs and the other CPU will be used by the BLAS and so on. So it's really trying to divide all the pieces horizontally and to give them a specific set of resources and not sharing all the resources of the node with every library. So this is a cool idea. Also, it will work well with workflow because it means that the jobs will start using a subset of resources. Then when it will need a specific set of other resources for a specific part of the application, it can just launch another job saying, okay, this job is, for example, only for GPUs. And then I will give him a CPU and the GPU to work and so on. Enabling such workloads in MPI leads to multiple questions. How to map programs in the machine, since now we really have to give some resources specific to each job on my workflow. How to discover reliability services, possibly cross job, and how to exchange data without remote state assumption. So what we are working specifically in this paper, in this presentation, is on the second aspect, which is how we can discover reliability services. So basically is when we are launching multiple jobs or when a job wants to launch another job, how we can do that, how we can do them connect efficiently, find them, and so have either better performances by composability of jobs. So first, let's ask how MPI can provide horizontal scaling. So what's existing today in MPI? Either you have multiple data, so you will use one launch with MPI run. Well, actually, it's MPI exec because what's the standard thing that you can do this is MPI exec. So you will launch multiple jobs, requesting a set of resources for each of the job, and they will end up in the same MPI convert. One other way to do that is using MPI spawn. So here, we are closer to a service way of thinking, since you will start a further job, and at some point, the job will start another job using API spawn. We create another set of resources. Then between the two, you will have an intercom linking the two jobs, and you can create a new common communicator using the MPI intercom merge. The last way to do it is using the MPI com connect, MPI com accept. So you will have two different jobs that will launch completely independently. Then at some point, one of the jobs will publish the information so that the other job can look up, try to connect, get basically an address to connect you. Then they will it will ask to connect, the other one will accept to connect, then we will link the two jobs together, get an intercom merge, and if you need the two parts really to completely discuss and not in a bipartite way, you will do the intercom merge and have a common communicator. Another way also of thinking that is now you have MPI sessions. So the thing is, when you are in pure MPI session styles, you can also create horizontal scaling because you will create, you will require resources based on some URI. So for example, let's say that you launch in the same job, but two sessions, one for the atmosphere app, the other one for the ocean app, then you will have complete separation between the two communicators. So we are really some separate set, but okay, I suppressed one on my slide. The thing is, you have really two separate connected graph, basically. But if you can create another session which will ask for the session to use, for example, the two core 0 of each subset here. So for core 0 and core 4, for example, then you will create I would say, an abstract link, not a direct link because sessions are not allowed to discuss together. So, but you will start with two distinct graphs that will be connected through the middle session. So what we worked on was a way to address processing globally in MPI. So to help connect it to distinct graphs together in on only one communicator, like when we do connect accept or a conspot. We really aim at simplifying the connection between different MPI applications. For that, we need a global addressing scheme that can be directly interpreted and recognized from any jobs. And so it will be really easy to connect to each other. In the rest of the world, when you think about that, these capabilities are obtained with TCP and DNS for name resolutions, basically using an URI or a URL that a human can recognize. Here, so our goal is really to define an addressing for MPI processes, global on the whole system, unique for each MPI process, and addressable by any other MPI process. So the first part of the work is really to define this unique identifier. So to do that, this is how we got the different pieces that will create the unique identifier. So you can see that it's cut in two parts. The 32 first bits is a set identifier, which will be composed of the user identifier. So any MPI processes belonging to a user cannot be mixed and connected to MPI processes of another user if you're launching multiple jobs on the same node. And also we have a set identifier, which is a random number when we store in the file system. So we have a unique way to identify what we call the set identifier, which is really how we will identify each group of processes. Then the second part inside this set is the way to just identify a process inside this set. So the process rank in the job will be here, the PMI rank that we have when we launch the job. The interesting thing is we can also create the communicator UID in the same way using the 32 first bits with the set identifier and then using the communicator local identifier. Of course, the communicator rank is still the same value because that's how it is defined in the MPI standard, it's an integer. So we cannot change that. But basically, when we create a new communicator and each processes and each rank, we have just a translation table to translate the communicator rank to the global process UID. So it is really easy to identify a process. And then what's happened is when we launch two jobs, we have two execution sets per job. So here we have the blue and the pink one, basically. For each execution job, at some point, a root process is elected. And when we try then to connect jobs, what we want to do, in fact, is just we can easily identify the root process of each job, which is the root process of each execution set, thanks to the 32 first bits, because it's the same. So when two processes try to connect through connect subsec, for example, basically we will just give the process UID and then get the set identifier from this process UID to directly connect to the root process of this UID. And so we can have really easily create a grouping together a process set in the a new communicator. The purpose of this is to quickly be able to connect two distinct graphs inside one, first to the root process, and then once we have this linked between the two distinct graphs through their root processes, we can create on-demand links between processes from the first graph. So for the first jump from processes to the other graph. Since we already have, we do that by using an overlay network that I will show you just after. And the idea is we have really simple way to connect the two. And then we use RPCs to travel through the job route to connect. And basically, through the RPCs, we can distance on the second process do both the put and get that is needed, so the connect and the accept. So the RPC has really the advantage of giving remote control to establish the connection propagates remote completion. So we've done that in MPC. So the overlay network that we are creating bootstrap it with a peer-to-peer topology. So we are using first PMI and TCP PMI to create our TCP overlay network with a Kademlia topology. So we'll show just after what is a Kademlia topology if you're not familiar with it. Thanks to this overlay network, it supports the routed remote procedure call, so routed RPC out of the overlay network to really facilitate this connection. Each root process that is elected on each set can list the sets and the root messages across the sets, so can really list how it can connect to the other graph. One of the big drawbacks is we have to recreate and to rebuild this network each time and not store it like PMI can do it. So just an example of what is a Kademlia topology. So Kademlia topology, basically for each process, each node is connected to the other node, which is the next powers of 2. So 0 is connected to 1, then to 2, then to 4, and then to 8. And if you do this for everyone, you will have a really interesting connected graph since you will have a logarithmic diameter. So it's really efficient. Also in MPC, we implemented a command MPC sets that will allow you, when you launch it, to identify all the sets that are running. So you will all the jobs with your graphs. And to tell you what is the command that was launched within that graph, what is the size of this graph. And here you can easily get this kind of graph, which is the connectivity between your jobs. So here you can see you have 3 jobs that are connecting through their root processes. And the dot in the middle is actually the common MPC sets, which also create the jobs and create and connect to the other jobs running. And this graph was obtained using the MPC sets and the output. Okay, so now the performance evaluation. So first, just an idea of how the Kademlia topology works. So on the left, you have the network radix in function of process counts. So you can see that it really follows the logarithmic function. And then on the right is just the average round-trip latency that you will have for routed RPC to reach one processes from the processes 0. So you can see that depending on where you are, since you have this kind of jumps because you're connected to power of 2. So of course, if you are 0, here it was for, I think 496. So if you aim for 2048, it's only one hop since you're directly connected to powers of 2. Okay, so we use this benchmark to evaluate if our idea of the overlay network was helping connecting processes and jobs with each other. So what we've done for our benchmark is we compare between with PMIX. So we put a barrier at the end and at the beginning to really measure the same things. For PMIX, we do the inputs, then a barrier, which will be disseminating or not, and then the n times k gets to get all the information and be able to connect. On the rotated RPC, we do the n times k on-demand RPCs to connect to each other. We use a figure of merit, which is basically the times divided by the number of connections that we want to do. So the first graph here compares PMIX to our router RPC using the PMIX altogether, because here we are inside one job. So PMIX are all the information inside the jobs. And when we do the n puts, then the barrier that we do is altogether. So it will be propagating all the information. And basically then the gets will be really easy to do, will be free because the information will already be propagated. We have different curves, which depends on the number of neighbors. So when you see here in blue 1, it's 1% neighbor with a number of neighbor between at least 2, up to 100, which is we have the 100% of neighbors. So it's a fully connected graph. What we can see is when we are inside one job, so we can use the PMIX altogether up until, let's say, between 10 and 20% of neighbors, how overlay network is better. So here the dashed red lines is 100%, which is the performance obtained with PMIX. So when we are under, then we are faster than PMIX. When we are over, we are slower. So up to 10%, we are faster. For 20%, it's quite the same. Over 20%, then here PMIX is better because of the whole gather, while we basically have to do an old tool to get all the information with the rotated RPC. So that's why we are slower. But on the other hand, when missing a word, so comparing PMIX not using the all gather, because here is different jobs. So the PMIX don't have the information to do the all gather. It has to connect to basically do an old tool to get all the information, basically the same as us. Well, we can see that pretty quickly we're using the overlay network because of the Kademlia topology. So we're also doing an old tool, but with rooted, with roots that are a bit better. Then we are faster than PMIX. And then after basically here the curve stops because with PMIX we had issues and it's kept on crashing because I think we put too much pressure on the guy connected. Yeah, okay. So here to conclude, our idea here was really to try to provide a better way to connect distinct graph of processes, basically to connect distinct jobs that you will create on the fly and need to connect, which really capture the, for example, a workflow way of using the jobs. So really trying to have MPI as services, having jobs popping up and then disconnecting, and you have to connect all the processes and the graph processes of all these jobs. So for that, we implemented an overlay network which used routed RPC to perform collective in cases where connection ratio is reduced. And thing is, MPI needs to evolve to provide horizontal support. And that was a part of getting there, of getting an easy way and a fast way to connect multiple jobs. So it will be easier to releasing MPI jobs as services. What is next? We want to continue working on composable sessions. I just gave a small hint on sessions on what we could do. So we want to continue working on that. Also, try to replace the expensive old tool at program start with overlay RPCs. And also with tools, we want to see how we could leverage all MPIT evolutions with a sideband tool. So basically having a specific overlay network for all the MPIT informations. So thank you. I will stop here. So thank you for your attention. If you have some questions, I think we have a few minutes left, not a lot. But
I think we have time for questions. Let's do. Any questions, folks? Questions?
Is there questions on the chat? No? Okay.
I don't think so. Is there a question? I had a quick question. So why, there are other low diameter topologies, why Academia?
Okay, so the logarithmic nature of the Academia seems really interesting. So that's really why we wanted to try that. Actually, it just also was kind of, okay, this is used for peer-to-peer, so it will really help to. Well, Academia it was used for peer-to-peer connection. We say, okay, it has been done for connecting a lot of people. So let's try how it can do on MPI, trying to connect a full graph on the fly. That's basically why we tried it, and we got good results. So that was a good idea.
All right. If there are no other questions, then another round of applause for Julien.
Thank you.